In healthcare facilities, ground fault protection is a critical safety measure. According to the National Electrical Code, specifically Section 517.17, from the 1999 edition, all electrical systems in patient care areas and associated equipment must have ground fault protection. This protection is achieved through a combination of equipment grounding, bonding, and ground fault circuit interrupters, or GFCIs. The key component for the proper functioning of GFCIs is the presence of a neutral conductor. GFCIs operate by detecting imbalances between the current flowing in the phase conductors and the neutral conductor. If there's a ground fault, some current will divert from its intended path and flow to ground, creating an imbalance. If this imbalance exceeds a certain threshold, the GFCI will trip, interrupting the circuit and preventing potential electrical hazards. Consider a scenario where the incoming service to a facility is a 4-wire, 3-phase system with a neutral, and it has ground fault protection. However, some of the branch circuits within the distribution system are wired with only 3 wires, meaning they lack a neutral conductor. If these 3-wire circuits feed a 3-pole transfer switch, the ground fault protection on those circuits will not function correctly. The absence of a neutral conductor prevents the GFCI from effectively monitoring the current balance and detecting ground faults. To rectify this situation and ensure the proper operation of ground fault protection, there are 2 primary options. Firstly, you can extend the neutral conductor. This involves running a neutral conductor from a point where it is available, such as the incoming service panel, to the branch breakers and the transfer switch. By providing a neutral path for the GFCIs, this option enables them to function as intended, detecting imbalances and tripping in the event of a ground fault. Secondly, you can replace the transfer switch. This involves replacing the existing 3-pole transfer switch with a 4-pole transfer switch. A 4-pole transfer switch allows for the connection of the neutral conductor, providing a complete neutral path for the GFCIs on the affected circuits. This ensures that the ground fault protection system can properly monitor and respond to ground faults. In most cases, extending the neutral conductor, the first option, is generally the more cost-effective approach. It directly addresses the issue of the missing neutral path without requiring a complete replacement of the transfer switch. However, there might be situations where replacing the transfer switch, the second option, is more appropriate. For example, if the existing 3-pole transfer switch is part of a larger, integrated distribution system and needs to be compatible with other components, replacing it with a 4-pole switch might be necessary to maintain overall system compatibility. Several additional considerations are important to keep in mind. Firstly, ensure that the transfer switch, whether it's the existing 3-pole switch or a new 4-pole switch, is properly rated for the load it will be serving. The transfer switch's amperage and voltage ratings must be sufficient to handle the maximum current and voltage of the connected circuits. Secondly, verify that the main switchboard, branch breakers, and all other equipment in the system are properly rated for the voltage and amperage of the system. Using equipment with incorrect ratings can lead to overheating, equipment failure, and potential safety hazards. Finally, and perhaps most importantly, consult with a qualified electrician to ensure that the system is designed and installed in accordance with the latest edition of the National Electrical Code and any other applicable local codes and regulations. A qualified electrician has the knowledge and expertise to assess the specific requirements of the facility, design a safe and effective ground fault protection system, and ensure that it is installed correctly. They can also perform necessary testing and inspections to verify the system's functionality and compliance. It is important to understand the core principles of ground fault protection and the role of the neutral conductor in enabling GFCIs to function properly. However, designing, installing, and maintaining electrical systems in healthcare facilities is a complex and potentially hazardous task that should only be performed by qualified professionals. Consider a more detailed explanation of extending the neutral conductor, which is the first option. This involves identifying a suitable point in the electrical system where a neutral conductor is available. Typically, this would be at the main service panel or another panel board that is fed directly from the service. From this point, A neutral conductor of appropriate size must be run to each of the 3-wire branch circuits that lack a neutral. The size of the neutral conductor should be determined based on the calculated load of the branch circuits, in accordance with the National Electrical Code requirements. It's important to ensure that the neutral conductor is properly insulated and protected against physical damage. It should be run in the same raceway or cable assembly as the phase conductors of the branch circuit. At the branch circuit panel board, the neutral conductor should be connected to the neutral busbar. This busbar is typically grounded to the panel board enclosure, providing a path for fault current to flow back to the source. At the transfer switch, the neutral conductor should be connected to the neutral terminal. This ensures that the neutral path is maintained through the transfer switch, regardless of whether the load is being supplied from the normal source or the alternate source, such as a generator. Now let's consider replacing the transfer switch with a 4-pole transfer switch, the second option. This involves disconnecting the existing 3-pole transfer switch and removing it from the electrical system. A new 4-pole transfer switch with appropriate voltage and amperage ratings must be selected. The ratings of the new transfer switch should be equal to or greater than the ratings of the existing switch. The 4-pole transfer switch should be installed in accordance with the manufacturer's instructions and all applicable electrical codes. The phase conductors from the normal source and the alternate source should be connected to the appropriate terminals on the transfer switch. The neutral conductor from both the normal source and the alternate source should be connected to the neutral terminals on the transfer switch. The grounding conductor should be connected to the grounding terminal on the transfer switch. After the transfer switch is installed, it should be tested to ensure that it is functioning properly. This testing should include verifying that the transfer switch transfers the load between the normal source and the alternate source correctly and that the neutral path is maintained during the transfer. Additional considerations related to ground fault protection in healthcare facilities include the following. Firstly, regular testing of GFCIs is essential. The National Electrical Code requires that GFCIs be tested periodically to ensure that they are functioning correctly. This testing should be performed by a qualified electrician and should include using a GFCI tester to verify that the GFCI trips when a ground fault is simulated. Secondly, proper grounding and bonding is crucial. Grounding and bonding provide a low impedance path for fault current to flow back to the source, which helps to ensure that GFCIs trip quickly and effectively. All metallic equipment in the electrical system should be properly grounded and bonded together. Thirdly, coordination of ground fault protection is important. In systems with multiple levels of ground fault protection, it is important to coordinate the settings of the GFCIs to ensure that the GFCI closest to the fault trips first, minimizing the extent of the outage. Fourthly, documentation is necessary. Complete and accurate documentation of the ground fault protection system should be maintained. This documentation should include drawings showing the location of all GFCIs, the settings of the GFCIs, and the results of all testing and inspections. Fifthly, training is very useful. All personnel who work on or maintain the electrical system in a healthcare facility should be properly trained on the principles of ground fault protection and the operation of GFCIs. Training should include instruction on how to test GFCIs, how to identify and correct ground faults, and how to maintain the ground fault protection system. Here's a simplified way of considering the installation of ground fault protection and ensuring its proper operation. Firstly, assess the existing electrical system. Determine if the system has a 4-wire, 3-phase service with a neutral, and identify any branch circuits that are wired with only 3 wires. Secondly, determine the code requirements. Consult the National Electrical Code, specifically Section 517.17, for healthcare facilities, and any applicable local codes to determine the specific ground fault protection requirements for the facility. Thirdly, decide on a solution. Based on the assessment of the electrical system and the code requirements, choose the most appropriate solution, either extending the neutral conductor to the effective branch circuits or replacing the 3-pole transfer switch with a 4-pole transfer switch. Fourthly, implement the solution. Implement the chosen solution by either running a neutral conductor or replacing the transfer switch. Ensure that all work is performed by a qualified electrician and in accordance with all applicable codes and regulations. Fifthly, test and verify. After implementing the solution, test and verify that the ground fault protection system is functioning correctly. This should include using a GFCI tester to simulate a ground fault and verify that the GFCI is tripped as expected. Sixthly, document everything. Maintain complete and accurate documentation of the ground fault protection system, including drawings, settings, and test results. Seventhly, perform regular maintenance. Establish a regular maintenance schedule for the ground fault protection system. This should include periodic testing of GFCIs, inspection of grounding and bonding connections, and any other maintenance tasks recommended by the equipment manufacturers. The information provided so far should be considered in the context of a hypothetical healthcare facility's electrical system, so let's make some assumptions to illustrate the concepts. Assume the facility has a 480W/277 volts, 3-phase, 4-wire service. The main service panel has ground fault protection. There are 5 branch circuits that feed critical patient care areas. 2 of these branch circuits are wired with only 3 wires and feed a 3-pole transfer switch that supplies power to essential medical equipment. The other 3 branch circuits are wired with 4 wires and have functioning ground fault protection. In this scenario, the ground fault protection on the 2 3-wire branch circuits will not function correctly. To correct this, you could choose to extend the neutral conductor. You would need to run a neutral conductor from the main service panel to each of the 2 3-wire branch circuits. The size of the neutral conductor would need to be calculated based on the load of the branch circuits, and it would need to be installed in accordance with the National Electrical Code requirements. Alternatively, you could choose to replace the 3-pole transfer switch with a 4-pole transfer switch. This would allow you to connect the neutral conductor from both the normal source and the alternate source to the transfer switch, ensuring that the neutral path is maintained during the transfer. After implementing either of these solutions, you would need to test and verify that the ground fault protection system is functioning correctly. This would involve using a GFCI tester to simulate a ground fault and verify that the GFCIs on all 5 branch circuits trip as expected. In addition to these specific solutions, it's also important to ensure that the entire electrical system in a healthcare facility is properly grounded and bonded. This includes grounding all metallic equipment, such as panel boards, conduit, and enclosures, and bonding all non-current carrying metallic parts together. Proper grounding and bonding helps to provide a low impedance path for fault current to flow back to the source, which helps to ensure that GFCIs strip quickly and effectively. It is important to note that the specific requirements for ground fault protection in healthcare facilities can vary depending on the type of facility, the type of patient care being provided, and the applicable codes and regulations. Therefore, it is always essential to consult with a qualified electrician to ensure that the ground fault protection system is designed and installed in accordance with all applicable requirements. Here's a practical example to further illustrate the concepts. Imagine a hospital operating room that is supplied by one of the 3-wire branch circuits discussed earlier. The operating room contains sensitive medical equipment such as heart monitors, ventilators, and surgical devices. Because the branch circuit is wired with only 3 wires, the ground fault protection on that circuit is not functioning correctly. If a ground fault were to occur in the operating room, such as a short circuit in one of the medical devices, the GFCI would not trip. This could result in a dangerous situation for the patient and the medical staff. The fault current could flow through the patient's body, causing electrical shock or burns. Alternatively, the fault current could damage the medical equipment, causing it to malfunction or fail. To prevent this, it is essential to correct the ground fault protection deficiency by either extending the neutral conductor to the operating room branch circuit or replacing the transfer switch with a 4-pole switch. Once the ground fault protection is functioning correctly, it will be able to detect ground faults in the operating room and trip the circuit breaker, interrupting the flow of current and preventing potential hazards. Consider a situation where the cost of implementing each solution is factored in. Extending the neutral conductor might involve running new wiring through walls and ceilings, which can be labor-intensive and disruptive to the facility's operations. Replacing the transfer switch might involve a higher upfront cost for the new switch, but it might be less disruptive to install and could provide additional benefits such as improved reliability or functionality. Ultimately, the decision of which solution to implement should be based on a careful evaluation of all the factors involved, including cost, disruption, technical feasibility, and code compliance. Always prioritize safety and ensure that the chosen solution provides the required level of ground fault protection for the healthcare facility.